Every year, hurricanes and tropical storms formed in the Atlantic slam into the eastern seaboard of the United States, causing billions of dollars in damage and taking far too many lives. These amounts of casualties have made it the topic of our project today. Virginia is home to cities like Norfolk and Virginia Beach, whose low elevations and water access make them very vulnerable to these natural disasters. In fact, according to Policy Genius, Virginia is in the top 10 states that experience the most hurricanes. This makes the topic of our project, hurricane trajectory predictions, a vital tool that could help our state better prepare for and predict when hurricanes will impact Virginia. We went about approaching this problem using an LSTM RNN. LSTM stands for long-term short-term memory and is a variation on recurrent neural networks. In a standard RNN, it has proven difficult to make predictions based on events that are not immediately in the past. For instance, it's tricky to predict the next few words in a paragraph or sentence if the context was not recently stated. This is known as the vanishing gradient problem, and LSTM is one proposed solution to this. In an LSTM, the network includes cells within the hidden layers of the network that have input, output, and forget gates. Because these cells are designed in a specific way such that their outputs fuel into each other's inputs, these cells allow the network to hold on to relevant information for as long as they need. LSTMs are practically useful in problems where we need to create predictions with time-based data that may have inconsistent intervals between these measurements. And this is exactly the type of problem we see in the hurricane trajectory prediction, and so LSTM is the perfect type of model that we can use to solve this problem. To tackle this problem, we need to train our machine learning model, so we need to use a database open to the public, which just so happens to be maintained by the Hurricane Research Division of the National Oceanic and Atmospheric Administration's Atlantic Oceanographic and Meteorological Laboratory, called the Atlantic HURRDAT-2, a repository location of the maximum winds, minimum pressure, and radial winds and cyclone shape for all known tropical and subtropical cyclones in the Atlantic. We then take this dataset and we allocate it into our algorithm so that it has over 50,000 data points that it can use. Using an existing framework as a baseline, the hurricane track latitude and longitude data was converted into a single grid ID variable to sequentially encode its location for the training model. Approximately 1/5 of the data available was held out to measure the performance of each experimental model created, while the remaining 80% of the data was used to train each model generated. We then use this data to find the best fit trajectory for the predicted path of a hurricane. After allowing the algorithm to run for a certain amount of time, the initial model using all of the location, pressure, wind, shape data, and other sets available yielded a root mean square error of approximately 0.104 and an accuracy of 67.2% on the holdout set. But we can do better than this. After tuning the model architecture and dropping the shape parameters for each row to avoid the curse of dimensionality, our final model yielded a root mean square error of 0.1004 and an accuracy of 74.9. With these results, the predicted grid IDs could be translated back into the latitude and longitude coordinates and used to predict where and when a storm will make a landfall, thus giving us our final algorithm. Looking back, the impact of models such as ours is wide-reaching for Virginia and other coastal states. The more accurate predictions we are able to make, the more time we have in advance to prepare for these storms. Time can mean everything when preparing for a hurricane, as it allows civilians to evacuate and the appropriate authorities to put a plan into action. Setting up shelters, boarding windows, gathering supplies, and more all could be more easily accomplished given a wider operating window that this algorithm can provide. Hopefully, this algorithm, along with the contributions of many others, can prevent millions of dollars in property damage and save countless lives in the long run. Thank you all for watching.